Good evening. Thank you for coming here. We are very excited about this meetup today to show you all what we have. Srini did an excellent job with going through the theory and telling us what machine learning is and what Spark MLLib actually is and how we can use it. I'm here today to go through some of the case studies that we have used Spark MLLib for. The first case study that we're going to look at today is Predict My Favorite Song. So Spotify has a huge database where they have a lot of song attributes they collect for all the songs that they have. Right? All of us at some point would have used Spotify. But when you do, you keep getting next songs that get play as you listen to the kind of songs you do. You get more, it learns better and it learns to show you or play the right songs for you. So that is mostly powered by machine learning. What I'm going to do here today is I have a data set with songs which have tags whether I like them or not. So based on that, there are song parameters provided by Spotify which gives you things like acousticness, tempo of the song and so on. So without me having to say it, will the machine be able to predict if I like a song or not, and how you go about building this system is what you're going to see in the first case study. The second one is customer segmentation. Customer segmentation in general is used a lot in the industry, right? It may be retail, online retail, wholesale. All of these guys would like to segment their customers to see how what their behavior is and so on. In general, segmentation can be done on three things. One is customer demographics, customer psychographics, or the behavior of a customer. Demographics is kind of a touchy field. You can't always obtain the right data or the right demographics data for your customers. It's more difficult. Psychographics is what are their likes, what are their hobbies, interests, and things like that, which is also very difficult to obtain unless you have surveys and so on to do. The third one, which is the behavior data which you can use for segmentation, is one thing that most of these companies already have. With what did they buy from them, how often did they buy, annually how much did they spend for different categories and things like that. So a lot of companies use customer segmentation on this behavioral data to make profiles or segment their customers in a way to better market their products to them. So one of those case studies is what you're going to see today is publicly available data of a wholesale company, and I'm going to show you how we can do that using Spark MLLib. Tools used. We extensively saw what Spark MLLib is. Srini gave a detailed outline of what it looks like. We're going to see that in practice today. And Spark MLLib, as he said, has 4 or 5 different ways you can access it. You can use Scala programming language, R, Python, Java, or SQL. Today we are diving into Scala. Scala is it's kind of object-oriented, like Java, at the same time it's a functional programming language as well. So it has the qualities of both, and it is one of the very popular programming languages that people use when they want to work with Spark. Advana is, so I'm not going to write the code right here for you guys for all of the activities that this case study entails. But what we are going to use is a tool called Advana. Advana is a web-based, GUI-based tool where it's drag and drop kind of a functionality which will actually generate the Scala code. So I'm going to use that so I can just generate the code, and then we can actually take a look at the code and see how it can be written. Any questions before I get into the demo, or no? Okay. I'm getting into Advana. So the first case study I'm going to pick up today is the customer segmentation, what we looked at. the data that we were talking about is from a wholesale customer. So I'm going to just drag and drop this data.
Can you tell us what environment you're running this in?
Sure. So this is, you mean the tool Advana is what you're asking about?
No, the hardware that you selected, AWS.
Oh, okay. So all of these data objects you're looking at here is in our AWS server. So you can, it's a sandbox actually. We have another tool we use called Plexa, where we do all the transformations of the data, prep it and load it in here. And we just connect this. Advana is, it is configured to look up all the data objects that are in that sandbox, and you can build your models in here.
So the data per se is in HDFS file system,
okay,
and the actual processing happens in Advana.
So this is the wholesale customer's data. I'm going to show you a preview of how the data looks like, so that when we actually go in and run the machine learning algorithm, we can relate to it. What we have here is the annual spend of the customers in the following categories. So you have fresh, which is the fresh produce, milk, grocery, frozen items, detergents, paper, and the delicacies. So this is the total spend this particular wholesale retail customer has from their for all their customers, and they're bucketed into two different channels and regions as well. But we are going to look mostly at these features: fresh, milk, grocery, frozen, detergents, and delicacies, to perform our customer segmentation today. And a lot of the feature transformation extraction capabilities that Spark MLLib has, we're not going to use a lot for this case study, but I'm going to show you a little bit more when we move on to the next one. But here I'm just going to use the vector assembler, which is something you have to use when you're when you're building a model in Spark MLLib. You need to assemble all of the features or all of the columns into one vector and provide it as an input to your MLLib model that you're building. So I'm going to use a vector assembler real quick. Go in here. And I'm going to call it the features, since that's the latest and greatest word. And then I'm going to simply use a clustering methodology. Your segmentation can be done using various techniques. I'm going to use clustering, maybe the k-means clustering to start with. And in here, I'm going to provide the name of the features column that it's going to use for building the model, and the name of the prediction column, so what the prediction column needs to be called, and parameters like the number of clusters you want it to create. The default here is 2, but let's create 5 clusters. And there are some other parameters which there are some default values that it takes. We can talk a little bit more about model tuning and everything later, but for now let's just run this and see what the code looks like. So now all the different components that the flow that Srini was explaining to us earlier in a very simplified form, you can see in this particular code that got generated. Is it visible?
Yeah.
So the first part, or this part, is where the data shell is getting created, which is basically going and retrieving the data that we are trying to read here, right? So it's doing a spark.read.format. It's a Parquet file from this location, which it's configured to read from.
So this is the machine generated code based on your drag and drop.
Sorry, what was that?
Is it machine generated code based on your
Yes. Yeah.
Is in R? This is R.
This is Scala.
Okay, Scala.
Yeah. And what I usually do is I create the code here. I copy it onto like a Spark notebook, and you can run it there too. But if you don't want to write all the lines of code, you can use this to generate the code for you. And the second step, if you see here, is the vector assembler. Remember, we were talking about Scala being object-oriented as well as partially functional programming language. So if you have a background in Java or any programming languages that are similar, you probably will identify the code that you see here. The vector assembler is created right here. So you have to define that object, and then you need to set all the inputs that it needs. So you see a set input column. These are the columns that we gave in the UI. We said we need to select all of these columns and create a vector. So that's what it's saying, and the output column is called features. So that's what is setting here, right? Then the next thing is the k-means clustering model. So this is the important part. How do we build this? So you have all the packages that you need imported, and then you also have this k-means model object that is being created here. And here is where you would set, the model has parameters that you can set. The model object has parameters that you can set, and those parameters are what we provided initially in the UI. But let's say you're writing this is what you would do. Set feature call, give the name of the feature column, set prediction call, the name of the prediction column, set k is your number of clusters, and all of the other parameters can be specified here. Right, then let's go back here. So now there's also a way you can go in here and look at the results. So let's just take a quick look at the results, and then I will show how you can create a pipeline as well for the same code. Since this is clustering, the first thing let's look at is the cluster sizes. We created 5 clusters for the data that we've given, and this is a result pane which basically lets you view the summary stats and other statistics and the results generated by that particular model, right? So there are 5 clusters, and it also shows the size of the cluster if you hover on each of them. And the other thing you could also see is, if you are clustering one, the other thing you would like to see is the scatter plot of your data points, how they look, right? So there is a 2-feature as well as a 3-feature cluster plot here. Let's see how the 3-feature one looks first. So if you look at this, you probably can notice the different clusters, how they're formed. This is actually a pretty good, it's a decent data set to observe the clusters. In reality, you would also do like outlier removal and things like that before you actually did the modeling, but in this case we didn't. So you're seeing some of the outliers classified as like this one is just the only black one, which is probably an outlier we should have removed, but that's taking it as a cluster by itself. So that's why we had one cluster with a very small cluster size. You can even dig into this and play around, but yeah. The other thing is, if we also would like to see is the summary statistics, right? When you build a model, you want to see what the statistics are. Like if you're building a regression model, you want to go see the p-values and things like that. So we can take a quick look at the clustering summary stats. And the feature, the scatter plot, especially for clustering, that plays a very important role, because they definitely like to see how their data looks like with respect to those features before they can make their decisions, especially for market campaigns and things like that. Right, so these are the summary stats for this. We said this was the number of clusters, cluster sizes, the compute cost, max iterations, and so on. Going back here, we spoke a little bit about pipelines earlier. So what do we do with the pipeline? I'm going to show you the code of a pipeline. Let me get one on to here first. So what the pipeline did is it put both of those vector assembler as well as k-means cluster inside the pipeline. Let's say I had outlier removal node, I had a dimensionality reduction node, and so on. And then I had a pipeline in it. It would make a lot more sense, and it would actually justify it, mainly because why we use a pipeline, as Srini explained. Now I did all of these process, all of the development to just build my model. Let's say I need to score my incoming data, like I get new customer data, I want to score it and see what cluster they belong to before I can make any strategic decisions. I need to score them, and to do that I will have to again prep the data to the same level before I can score them. Same steps have to be applied on the scoring data set before I can actually apply the model on it. So that's what that added work is what is eliminated by the pipeline concept provided by the Spark framework. And in this tool specifically, you can attach your scoring data set to the score node. Let's go get the scoring data set. Connection. And now if you go to the source code, earlier when we did the k-means, we saw that the k-means model had a dot fit, which created the model, and then we did a dot transform on the data shell, which was the data connected to the training node, right? So right now, since we are building a pipeline and we're also using it to score, you'll see the new pipeline gets created, and the k-means model itself is defined inside of the pipeline. Outside of the pipeline, the vector assembler is defined, but the dot fit is not there, which is what is used to actually build the model. You're only setting the parameters for this object, but you're not running the dot fit, which creates the model. That happens within of the pipeline. So if you come here, you see there is a new pipeline created, and then you say pipeline.fit, which means all of the components or all the models that are within of the pipeline need to be fit or created so that you can use it for transformation. And then finally you have the model.transform, and now you see there is data shell 2, which is your scoring input, which is basically used for scoring, to generate the scoring output. Right. I'll show a little bit more about how you can do model tuning and all of that. Any questions with this before we move on to the next case study? So the next case study, we spoke about this earlier. It's a Spotify classification problem that we are solving here. So if you look at this one, this is already pre-built. I'm not going to build everything out again, but what you're looking at here is Spotify data that I can show you a quick look at what the columns are and what it looks like as this runs, and we can see the final results. So this is Spotify data, which has the columns that we were talking about earlier. It has acousticness, danceability, duration, energy, instrumentalness, tempo, and so on, which show us, which basically are the attributes of a particular song. It also has the title and artist, which is a character, both of the character string variables. And the next step I'm doing here is string indexing. So what string indexing does is, in this case, artist is what I'm trying to index. So when you want to provide a character variable to your model building, you need to convert it into some form of numeric format. Srini explained it very well, but I'm just reiterating. String indexing gives the index to each of those values in that particular column, in this case the artist column. I'll very quickly show you what I've done with it. So here if I go in, I have the column artist, and I'm creating a string indexer artist, which is the indexed version of the artist. And then you can't, when you index it, if you have, let's say, 4 values in your artist column, it will be indexed as 1, 2, 3, 4. It's a categorical, and it doesn't really relate to each other in any way. So we need to encode it, for which what we have is called the one hot encoder, provided by, this is one of the feature transformations of capabilities of Spark MLLib. one hot encoder encodes this to a binary form that can actually be usable in your model, or the model can comprehend to what it means. So if I go here, you'll see I'm on that string indexed artist. I'm creating a variable which is encoded. I'm going to show you all the code for this, but I'm just going through this one. And vector assembler, as I said, it's combining all of the features together to create one vector which can be provided to your model building process. The next one is a dimensionality reduction, principal component analysis. It's also a part of Spark MLLib's feature transformation capabilities. The PCA, what it basically does is when you have a lot of variables, and if there are any two variables which are highly correlated, they could cause in overfitting or the model not being accurate. In which scenario you have to use dimensionality reduction of some form, like the chi-squared selector that Srini spoke about, or the principal component analysis. So in the parameters, I'm going and saying what are the features that needs to be given as an input to my PCA. And that's done. And then the data partition is splitting my data into testing and training. I have basically made a split of 70 and 30% training data and testing data, which is what is represented here. And then finally, the logistic regression model is, I have actually multiple. I have 4 classification models I'm using to classify as to whether this song is liked by me or not based on the past likes and dislikes I have in the data set itself. Right, let's go quickly to the source code before we go and look at some of the results. This is the data shell getting created, so the data is being read, and now string index are very similar to what we saw in the previous code. Is again, you're creating an object of the string indexer and setting all the parameters and doing a dot fit right here. And here I don't have a pipeline, so you have to do a dot fit at every object level, at every model level. Then I'm also using the one hot encoder, so I'm defining that one hot encoder model object and assigning all of the properties here, input column, output column, etc. And then I have the one hot encoder model dot transform giving string indexer as an input. So that's how you would take it from one step to the other. And then I have vector assembler, just like what we saw in the previous one, where we are giving all the input columns that it needs to combine to create the feature column, and that's what is happening right here. And this also has a model dot transform on the one hot encoder because it's taking the data from the one hot encoder, which is the previous step. Similarly for PCA, and this also has a dot fit and dot transform. And finally, all the models that we are running, the logistic regression model with all of these different parameters given, and a dot fit to create the model, and dot transform to actually transform the training data set and predict your prediction for the like or dislike in this case. And these are all some of the tool specific code you're looking at to see a preview and things like that. And then we have the decision tree, very similar to that. All of them have very similar, the code is written in a very similar fashion. You just have to call when you create this object, you just have to call the right model class that you're creating that object for. That's that. And then there is the model tuning we spoke about. I didn't apply any model tuning so far. We can look at that too, but before we do that, let's take a look at the results and see how they're performing. I have a misclassification chart which I think is very helpful to see how it classified and what it actually should have classified it as. In this case, since we're using binomial, you're going to see 2 classes, 0 and 1. This is not a multi-class classification. One thing I didn't probably show is for all of these transformed data sets, we're looking at the results in this tool, but you can also go to the the model itself gives you a summary object. So you can do that model dot summary object. That object has all of the parameters that we're looking here as visualizations in some form or the other. So this is the misclassification chart for the logistic regression. So if you look at it, these are the labels 0 and 1, and it's saying the blue part is the correct classification and the black is the incorrect classification. So for this example, it's about 30% inaccuracy or 70% accurate is what this model is, and you can check the same for all of the classification models. Let's go here, show results.
So we're running this on Spark environment, which is much faster than MapReduce. So how much slower would it be if we were using the traditional MapReduce?
So some tests have been made, and for comparable data, it has been found that Spark, when it runs in memory, it has been found to be 100 times faster than MapReduce.
Right. So data we're using is like 40,000 records. So in that size, are we going to see that much difference?
Probably not that much, because when you increase the data to millions and more data, then the speed will be more.
The volume of the data, as it is more, the benefit is exponentially higher too. So that's why this is mostly used in the big data applications as such. So this is the second model we are looking at, and this is slightly better. It's a decision tree model, and here we can see that it's the misclassification rate is way lower than the previous one, almost by half. So similarly, I think you get the point what I'm trying to say. You can go in and compare your models and all of that in here. And going back to the model tuning part in Spark MLLib, which is also a very interesting concept. When we first created the logistic regression, we gave it certain parameters, and we saw that in the code as well. When you created the logistic regression object, there was a dot set parameter 1, dot set parameter 2, and so on. Model tuning is basically saying, hey, I don't want to set one parameter for this. I will give you multiple, and I want to see different models created for different combinations of them, and then you evaluate and tell me the best model. So that is what model tuning is, and that's what this. I can show you how it can be done by using this. It will generate the code. Let's say you're using cross-validation, then I can also select, since this is a binary classification, what are some of the evaluators. And what you're seeing here is also what Srini showed. These are the 3 kinds of evaluators that are provided by Spark for classification and regression kind of modeling. And also when you model tune, you can specify based on what evaluator you used. You can also specify what evaluation metric you want to use. So what is the metric based on which you're going to compare these models on. So that can be chosen. And once that is done, you can, this actually creates a parameter grid, which I'll show you in a bit. But let's say convergence tolerance is one of the parameters I want to change. I can say create models with 0.001 and create models with 0.002, right? And click OK. I can create even one more different parameter. Let's say fit intercept. And then if you run this, so now if you look at the source code here, you'll be able to see that a param grid gets created. So that's basically how you do your model tuning. You need to create a param grid, which is right here. So I gave 2 different values for convergence tolerance here, and then 2 different values for the fit intercept. Now it takes a combination of these 2 and builds that many models and compares their performance based on the area, the ROC, which is what we selected, to create those models and give you the best one. So that's how model tuning is done. This is an example for logistic regression, but all of the other models that we see here can also be tuned using the similar methodology. Only if it was based on what technique you're using, the evaluators would change, and also based on if it's binomial, multinomial classification, the evaluators will change as well. That's all I have for today for the two case studies. If you have any questions for me or for Srini, we can take it now.
On your flow diagram,
Yes.
the data,
Uh-huh.
the data partition, you set those to percentages.
Yes.
Is that randomly splitting the vector?
So that is based on, in statistical modeling as well, you usually split your data into training and testing. So training data is what you use to build your model, and then you
I
validate.
understand that,
Yeah.
but I saw that you said the training data, or the training, one was 70%, one was 30%. Is it randomly pulling
Yeah.
data sets out of the input vector to create those, to do that split? And
Yes.
does it do it once? Does it do it every time you run?
Oh, if every time I run this process?
Yeah.
Yeah, it redoes it every time I run
So
the
it
process.
reshuffles
Yes.
that split. Okay.
And it does by random, correct?
We have a different Spark library, right? So versions control we have, right? So how are you going to accommodate that features in this tool?
When we developed the tool, we developed it with available Spark version, and as and when new features and capabilities come in the newer Spark versions, that will get added to this tool.
Okay, do we need to modify any logic
No,
or value?
as a user, you don't need to do anything. You will get more and more features as and when they get available in Spark machine learning.
Oh, yes.
Let me preface this by saying I'm definitely the least technical person here. But one common complaint I hear about this kind of stuff, machine learning, is the term overfitting or data mining. What's your argument against that?
Oh, sorry, did you say overfitting?
Yeah, overfitting and data mining.
Overfitting in data mining. Let's take a scenario, right? I want to classify whether I like a song or not. I want to predict that. But let's say in my past data, I have 80 songs that I like and 20 songs that I don't like. So as and when new data comes, if I predict all the songs as I like, any data that I come, I will predict it as I like that song. I will get 80% accurate because 80% of my data is something that I like. So I will get 80% accuracy, but that is not correct. So that's why we do the false positive, false negative, and area under also there are some metrics to see that just having an accuracy doesn't, 80% accuracy doesn't mean that whatever is being predicted is correct. So each and every row needs to be taken into consideration, and based on the characteristics, it needs to be seen in the past to see whether it matches to that particular correct prediction. So overfitting in this example would be just taking it and predicting it as I like that song because that has been my majority observations in the past. So that should be something that developers like us normally look into. Just that if the R squared or any metric is very good, that doesn't mean that it's wrong. There are additional metrics, detailed metrics available to detect these kind of overfitting scenarios.
And the other thing is if there is highly correlated variable with your target, can cause overfitting too. Like in this example, let's say I always, my data set shows that 90% of the times I liked the song by this particular artist. Then next time I'm over, there is another song from this particular artist, it will tend to say it is a like without considering the other parameters of the song. So that, yeah, that it's also some of the things that you as a model developer should take care of, eliminating high correlation with two variables, two independent or two features, as well as with the target variable.
Okay, so I guess my follow-up would be, so the machine isn't entirely running autonomously, like you are having to check up on it to see if there's spurious correlations in there, right?
No, the machine will tell us that these are really correlated, and then we as a user or something, the machine just does it and develops the model. So as and when the new data comes, the model of coefficient, say how much each parameter affects my like or dislike changes. So that is the part that the machine does on its own, learns on its own. Reading that model and interpreting it is something that we need to do. We still need to do. The user still need to do. The machine knows that machine will give you the results. It will give our area under ROC as a metric. So we need to see and interpret whether this makes sense or not. That is still up to the user.
All right. Great.
Any other questions, or we are open for discussion too if anyone has anything interesting to share.
One question about classification model. In general, which classification model you would prefer to use in MLLib? So we have random forest, we have
Similar,
multiple,
right.
K-means clusters.
Similar to what Srini was saying about regression, the gradient boosted and the random forest classification models are very popular. What I would pick for a particular problem would be obviously based on the performance of the model, but those are the very popularly used. Even in this example, the one that I just ran, if you look at it, the performance of the gradient boosted tree is way more than the logistic regression itself.
Yeah, to add to what she says, those two models have consistently been found to give the best results. But in terms of the flip side of it is that they are process heavy. They have lots and lots of steps, so they may take some more time, and depending on how much data you have, they may take more of processing power. So if these are okay, the processing and the time is not a consideration, then those two are probably the models to go to.
Thank you.
Mm-hmm.
So with the tools like the Ghana, seems like I really don't have to master the language like Scala.
Yes.
I just got to understand what algorithm does
Right.
and understand the data, and the tool usage is pretty good.
Right. Because the technology keeps changing very fast. So if you want to use the best and the most efficient technology that is available at that point in time, you have to keep upgrading yourself. So the tools like this are really helpful to, step you up and let you actually do what you want to achieve.
One more question.
Sure.
So let's say you let a model run, and then you're going to let it go on for another month, let's say. Would you judge a model by its predictive ability to judge that next month, or at the end of the month, would you say, okay, this new model fits the past state, but probably not working at the best? Which gets a higher weight, a model's ability to predict the future or a model's fit to the past? I guess is probably the best I can explain.
Yeah, you're right. So when a model is developed or when the model equation is first generated, it is generated based on looking the past data. And that's where its importance stops. So after that, as and when each and every new data comes, the model gets evaluated for each and every new data point. So let's say it's up to a company to decide. So they may study the next 3 months or next 6 months or next 1 month of data to see how the model is behaved based on when the model was developed, it might have say 80% accuracy, and but the business condition might change, the environment may change, the preferences may change, the variables that are used might no longer be useful. So normally companies, what they do is they study the future results of that particular model that were developed, and who may know, probably new variables need to be introduced to the model to make it more effective.
Yeah, and adding to that, there is a concept of feedback, right? So your model predicted something, Whether that is right or wrong, whether the model did a good job or not is a feedback given back as another variable which can help the model learn and become better. So over time, the accuracy of it improves.
Does that answer your question, or what are you looking for?
I'm not sure. I don't know.
Normally in practice, what we do is, as many companies study the model once it has been implemented for say 2 months, 3 months, 6 months, and then re-evaluate the model's accuracy once again. And if needed, it needs to be redone.
I guess my skepticism would be like they're constantly upgrading the model to explain the past, but it's not necessarily going to be more accurate for the future.
Yeah, statistics.
You're picking stocks.
No, like if your model say fixed and said, hey, this stock is going to go up by $10 by the end of the month, but it didn't. You're going to tell the model it didn't. So it corrects itself and it learns that it made a mistake by predicting that. So the pattern that I thought was right is not right, is what the machine learns.
I mean, I don't even dominate the conversation.
Yeah,
That's okay.
normally predictions, particularly in supervised learning like regression classification, are done on the basis of past data. Without that, there is no basis to predict. In unsupervised learning, you don't need anything to learn from it. You can group into clusters or do some outlier analysis, but in others, you need some basis to learn and to predict. That is the past data that is available. Sure, your point is valid in the sense the environment keeps changing. So the practical answer to that is the model has to be reviewed at regular intervals.
And plus the accuracy is never 100%, and if it is, it's not a full model.
Sure.
It would
But
be called.
as to what you said, we can have that feedback loop back into the model so that that variable will also be considered, and the weights given to say the different attributes can be changed on its own.
So the framework.
It should be more dynamic. The weights can be more dynamic in the sense that you cannot have a period of 3 months, or like you cannot stick to something for a longer term. You should kind of change the weights, keep changing the weights based on the various environmental factors.
The framework, based on your graphical tools, allows you to set up, I don't want to use the word pipeline because I think that means something different here, but just data flow through your analytical process. Is there support for incremental updates? So like if I just add 10 records to the input, does it have efficiencies to make sure that you don't reevaluate the entire input?
For scoring, you mean, or for building the model?
All the way through the data flow model.
So this tool, what you're looking at, is not a ETL tool. It's like a data scientist uses to build his analytical models, kind of a tool. The one that you looked at.
Okay.
Right. So there is the data.
It's more like a research tool then to get you the right model.
It is a model development.
Model development tool.
But to your question, if you use 10 records as opposed to say 10 million records, the amount
No, let's say you had 1,000 records, and then tomorrow I get 10 more new records, or let's say it's 1,000,000 records, and the next day I get 10 new records. Do I have to rechurn that entire stream, that data flow diagram, to process 10 new records, or is there an incremental capability?
I think he says like model like Kafka, like pointers.
Yeah, I guess I understand what you're saying. So there are two things here. You may choose to develop the model. One is the model development process, and one is the model scoring process. Example is credit rating. Okay. How does everyone's credit score get fixed? So there's some model happening in the backend, and everyone's credit is determined based on some parameters, say like my past spending and so on. And as and when a new person enters the system, based on those spending patterns, his credit score gets determined and renewed. So there is the model development part and the model scoring part of it.
Alright.
So the scoring part can be incremental. You can score how many other records you want.
I'm just
That's
curious,
Mhm.
how many, okay, you created a model
Mhm.
that does a good job of predicting. How much time do you spend with creating, having a third party or another person in your office independently create their own version of the model so that you can compare the accuracy of model A versus model B versus model C? Because it seems there are a lot of mathematical methods, the parameters you were using, and I'm just wondering how you decide between models. Let's say you have A and B and they come to different conclusions.
Yeah, as she showed, if we can use say 5 model, 5 models or 2 models or 3 models, and each of them gives some statistics at the end of their run. So we can we can see each of the statistics. They have the prediction accuracy, they have false positive. There are lots of metrics that can be used to measure the accuracy of a particular model. Considering whether I have, let's say, classification, whether I have classified it true as true, false as true, false as true, false as false. There are lots of parameters with which it can be evaluated. So each model gives out statistics also at the end of its run. So you have 3 models and its its related statistics. You can look at that and you can make a decision for yourself.
Yeah, there are metrics like root mean square error, absolute RMSE, root mean square error, MSE, MAE. There are different metrics that is given by the model. When it runs and it calculates, if you run the same data with 2 models, it will give you the statistics. And that is the metric we use to compare 2 models, whether it's built by 1 person or 2 people.
So
whatever
as long as
has-
the core statistics of each model are coming out the same, then each model should be equally valid.